Okay, this is team B6, and we're just going to go over our tank problem real quick. The first step was to create a new tank problem. So we use the format given previously in this course, and we just kind of change the numbers to uh, make it a new problem we can resolve.
So to solve the tank problem, once we had it all wrote up, the first part is to break it down by tank. So you see the A prime 1 there. The first part of that is the volume flow rate going into the tank multiplied by the concentration flowing into the tank. And then the second part, the 3 plus 5, is the volume flow rate flowing out of the tank. And then that has a concentration of the first tank. And then the last part, the plus 6 A2, is the concentration flowing into tank 1 from tank 2. So it has a concentration of tank 2. And a similar thing is what's going on for A prime 2 and A prime 3. And then basically you just consolidate that into one matrix, which is that A matrix. And then the B matrix next to it is the volume flow rate entering the tank times the concentration coming from outside. So for tank 1, that's 2 cubic meters per hour divided by 9 grams per cubic meter. And then for tank 2, since there's nothing coming in from outside, that's 0. And then for tank 3, there's 6 cubic meters per hour coming in times 5 grams per cubic meter. So that's 30. Then basically all you do is you solve that equation below it, that negative, or that A times Y equilibrium plus B. You can simplify it to negative B equals A times Y equilibrium. And you can just simply solve that using Mathematica, using that linear solve command. Then that Y equivalent variable gives you the equivalent masses in the tank. So 25.82 grams, 28.03 grams, 31.45 grams. And then the last part to do is to solve for how long it takes the tanks to reach steady state values. And that can be found using the eigenvalues of the system. So all you have to do is, we did it in Mathematica, you just find the eigenvalues of that A matrix, and then the smallest eigenvalue, which in our case was negative 0.547, that's your slowest decay rate. It's e to the smallest eigenvalue times t. And that's how you solve it.
And then I went ahead and plugged all of that into Mathematica, and just kind of checked his work by doing the exact same thing, getting the eigenvalues, using linear solve and such, and then creating a graph that shows time versus the grams of concentrate.
And once that graph was made, I looked at it, and it showed how the concentrate over time in different tanks, and these all each their respective equilibrium points of 25.8, 28.0, and 31.5 at their own respective rates. And for each of the tanks, they were hitting their equilibrium point around the 4 to 5 hour mark.